Hello, everyone. Welcome to another episode of Q&A about the future of science and technology. I am still not in my natural habitat, so technical things could go wrong here. All right, let's see. All kinds of questions that we have saved up here. One from Pavel here. Can AI be swallowed by more advanced AI by feeding it virtual input? The motivation could be increased efficiency of larger AIs. Well, let's see. I mean, the question is, computation can do all kinds of things. The issue is to align computation with the kinds of things that we humans care about and want to do things with. And the main sort of idea in modern times is sort of train the AIs with lots of material made by humans. And, there's maybe, I don't know, 5 billion, maybe 10 billion web pages that are sort of reasonably human written. Maybe if you include all of the sort of hidden stuff, there's maybe 100 billion pages worth of things humans have written. There's zillions of videos, things like this. There's lots of material that kind of shows what we humans care about and kind of paints the picture of the kind of human relevant world. And that's a place where if you want AIs to do kind of human relevant things, then you've got to kind of feed them human relevant training material that they will then imitate, so to speak. If you want them to do things that are related to, for example, the way the physical world works, then having them observe the physical world and say, oh, I've grown up learning about how chemical reactions work or how proteins fold or something like this. And that's my experience of things. There's a question, it's not completely obvious, to what extent the idea of just train with what's already known is enough to tell you what will come next, so to speak. With a lot of the things in the kind of human world, what we're finding is that we humans, possibly because our brains are not that different from neural nets that are sort of put into AIs, that the things that kind of we care about and that we are able to do are things that can readily be reproduced by kind of a trained neural net kind of approach. Whether that's true of the things that exist in the physical world is much less clear. It's a little bit complicated because there are things that are intrinsic to the physical world where the physical world is doing what it does. And there are aspects of the physical world that we humans have decided we care about. Like, for example, if we look at, I don't know, clouds in the sky, the detailed shape of clouds is something that we humans don't usually make much comment on, other than to say, that one looks like a chicken or something. But that's something. But on the other hand, the question of, is it raining right now, is something that we humans notice. And so it could be the case that even though the underlying physics that's making the billowings of the clouds and so on is not something that is readily AI-able, so to speak, that is readily sort of extrapolatable from training data, that it's still the case that something like, will it rain or not, is, and that's the part we humans care about. So this question about whether sort of things in the physical world are what one might call sort of AI-able, is it could be the case that at some intrinsic level they're not. In fact, that's my belief, is that they're not, for all sorts of reasons, but that it's possible that the ones of human relevance are more likely to be. I'm not clear whether they are or aren't, but that's not something to ask about. Sort of the underlying processes. We're running into this phenomenon of computational irreducibility that I seem to talk about a lot and that I kind of came up with in the 1980s. This idea that just because you know the rules for a system doesn't mean you can immediately kind of jump ahead and say everything about what the system does. You are, in general, have to just go through sort of the irreducible computational process of seeing each step of what happens. And if you're an AI that's sort of really trying to just say, is this something a bit like what I've seen before? Oh, then I know what's going to happen. That's not good enough. If you have computational irreducibility, you have to follow the steps, and there will always be surprises, and those surprises will be things you can't deduce from just saying, well, what have I seen before? Let me train on what I've seen before. As a very practical matter, I was just looking actually at the ability to predict like computational processes like cellular automata with things like neural nets, transformers, all the fancy technology and so on. And the answer is, it does kind of sort of okay in some cases. And when things get complicated and when sort of unexpected things start to happen in these computational processes, the AI predictors just sort of fall over and don't work. Now, there are all sorts of questions about what it's going to take to kind of get to different levels of kind of sort of human-like performance. I mean, that's a thing often of interest to us humans, is can we get an AI to do human-like things? Again, separate from, can we have the AI predict the positions of planets or something at some point in the future that is driven by physics? Can we get an AI to have human-like performance on telling apart pictures of cats and dogs? That's something where sort of the test is, can it emulate what we humans do, not can it follow what the physical world does? But again, more complicated in the case of the physical world is often what we want is not just the raw physical world, but the physical world as perceived by humans in some way or another. So I think we can kind of ask about all these different things about what's possible and what's not. I think one of the things that was obviously the big surprise of a bit more than a year ago now was the whole ChatGPT story of, gosh, you can have an AI that produces kind of pretty human-like language. And sort of, why does that work? How does it work? And I think the realization is it probably means that human-like language isn't as kind of complicated as we thought it was. It has more regularities that we perhaps should be embarrassed for not having noticed in the past. And I think that same thing can be said about a bunch of the places where sort of there's been success in where the AI has been able to sort of jump ahead and do things that seemed magical to us. It's like, well, that's because we didn't notice something that we could have noticed, that human brains could have dealt with. We just didn't happen to go in that direction. So, there are all sorts of questions about, all sorts of questions that raises. Like one question is, okay, so if the AI notices these sort of regularities in the world that we didn't notice, in a sense, science is about recognizing those regularities. So is it possible that the AI can sort of find regularities that will kind of drive forward science? Here's a couple of issues with that. One issue is, it's one thing to say, yes, I know what's going to happen. I have this black box model that I sort of feed the input into a neural net and it says the answer is going to be 3 or something. That's sort of case number one, where it's kind of a black box thing. Case number two is, I can tell kind of a human narrative, or I can derive it's going to be the number 3 with all kinds of human steps inside there. And I think it's there are plenty of cases, particularly in technology, where getting that camera to focus correctly on the object of interest in the image, it doesn't matter whether there's an explainable algorithm for doing that. It's something where when trying to achieve a technological purpose, that's what we want. It's, I think, less satisfactory in some cases if you say, well, why does this, if you're trying to have science be this kind of this way of kind of taking what science at some level, natural science at some fundamental level is taking kind of the complexity of the world and figuring out how to make a narrative based on that sort of addresses the main things that are going on in a way that sort of fits in our finite minds. That's kind of the key activity of natural science, is to do that. And in a sense, by saying, well, we just have this black box, which can say this is what's going to happen, but there's never going to be a human level narrative about how that works, isn't our traditional view of how natural science is supposed to be set up. Doesn't mean it's not useful, doesn't mean it's not, but it's different from what's been done in kind of natural science as it's evolved. Now, it has to be said that natural science as it's evolved kind of, in a sense, is evading computational irreducibility. wherever you say, well, you just have to run the system and see what it does, that's precisely saying there isn't a narrative that can be sort of a reduced narrative that we get to stuff in our brains that tells us what's going to happen. So I think this question about sort of when can we expect that sort of you can just learn from experience and see what's going to happen, and whether you can do that for systems in general or for the aspects of systems that we humans care about, those are lots of different kinds of questions. And another issue is this: maybe it's the case that if you're using something like a neural net and you're trying to take all of this sort of data about what happens in the world, and you're effectively making a model for that. You know, in a vastly simpler case, when you make a model for something, you might fit a mathematical formula to some data, and you might say that's our model. In the case of a neural net, you might be fitting, in the end, you are fitting a mathematical formula to the data, but it's a formula with 100 billion parameters in it or something. And it's a formula that has a particular structure that corresponds to this neural net. And there's kind of the question of, well, if you have a model of that kind, sort of how big a model do you need to be able to fit this or that kind of thing? So for example, let's say we're talking about mathematical formula models. That's often the domain of statistics. It's kind of like, oh, is this thing fit by two Gaussian distributions or something? You know, a formula that involves, let's say, you know, 4 parameters or something like that. Is that a decent fit to what we're seeing? You know, can we say, I don't know why I'm thinking of this case, but the law of friction, for example, you know, F equals the mu times n. You know, it's a linear law. The frictional force is linearly dependent on the normal force. That's a very simple model. It's not precisely correct, but it's a good approximation for many purposes. And the fact that that whole collection of sort of physical phenomena is modelable with that simple linear formula is an interesting fact. Now the question is, if you say, well, let's take human language, for example, how big a formula do we need effectively to do predictions, to model human language as human language is typically used? And the answer we know from ChatGPT is, with 200 billion parameters, we can do a reasonable job of sort of essay writing type human language activities. And there's sort of a question of is that, how does that 200 billion parameters or something, how does that kind of relate to what human language is? And for instance, could it be the case that there is sort of a point, a threshold at which you suddenly start to be able to do human language-like things? Oh, if we only had 10 billion parameters, we'll never get there, and so on. Now, there's a little bit of kind of circumstantial evidence about these kinds of things. So if you look at the history of machine learning, for example, there have been these particular times when sort of major advances were made that sort of vaguely corresponded to the amount of training time, the size of the neural nets, these kinds of things. The sort of the early efforts in doing, you know, can we recognize, you know, digits from 0 to 9? That was, you know, 1980s and so on, even earlier than that. Can we recognize, you know, 5,000 different kinds of images? That was 2011, 2012. You know, there are these thresholds that seem to be somewhat associated with the sizes of networks and the amounts of training data and so on. And so one of the things that's obviously an interesting speculation is, if you want to get to the point of having reasonable human language-like stuff, there's a threshold. I tend to think the threshold is considerably lower than the 200 billion parameters, because that happens to sort of package in a lot of detailed knowledge about the world that you don't really need to have good sort of common sense kind of linguistic capability. But maybe it's a 10th the size. Maybe it's you know, 50th the size. It's probably not a million parameters. That's probably not enough. So then the question would be, if we look at kind of the history of biology and we say, okay, you know, the great achievement of our species from a couple 100,000 years ago, or whatever, was we got human language. And notably, another great feature of our species is we got a bunch more neurons in our brains and more structure in our brains. And is it conceivable that there is a threshold at which you can have sort of reasonable human language? I don't know. I think that you could ask the question, typical human languages have, 30,000, 40,000 words in them that get used. I think that's true of all human languages. I'm not sure. I think that's true of the 7,000 or so extant human languages. I think that's true of all of them. Now, there are sort of constructed languages that have many fewer words, but there are fewer things you can say about the world with those constructed languages. You can even have ones down to a couple of hundred words, and you can have a kind of general pleasantries discussion with those languages, but you can't have for example, the conversation we're having right now would not really be accessible to a language with 200 words in it. Now, it raises the question of, if we scaled up, if we had a language with 1 million words, could we express a lot more kinds of things than we can express in our language with 40,000 words or whatever? Could we, could it be the case that insofar as we might talk about philosophy with our 40,000 word language, if we had 1 million word language, that we could have a completely different level of discourse about things? Well, I don't think we know, but there is this possibility that, for example, getting to kind of reasonable human language requires some threshold, and maybe there's another threshold higher up where we get to something a sort of superhuman language. You could argue both ways on this. I think one argument against it would be the phenomenon, the principle of computational equivalence, phenomenon of universal computation, and so on. That's a place where if you want to sort of get something that can do arbitrary computation, you say, well, I've got to add all these capabilities to the system, and I've got to make a Turing machine. We know from my efforts and so on from the mid 2000s and this prize that we had for, is this Turing machine the simplest possible universal Turing machine? Answer, yes. We know that the simplest possible sort of Turing machine that can do arbitrary computation is this absolutely tiny thing with 2 states and 3 colors. So, but sort of there's this question of, once you've got to the point where you can do universal computation, then there's no further sort of fundamental computational sophistication you can get beyond that. And in fact, it could be the case that if you're trying to do these things, let's say with a neural net, that it's incredibly inefficient, and that the neural net has to just go sort of, do all sorts of handstands and so on to, cascades of handstands, so to speak, to be able to get to the point of doing what, if you represent it a slightly different way, will be a rather straightforward piece of structure, so to speak. But that, so the argument would be, once the neural net, by all kinds of stuff, has been able to get to this sort of universal computation point, then computationally it's in principle able to go further. Actually, neural nets aren't good universal computers in the way they're usually used, because there's this kind of, one of the features of universal computers is they can kind of run with arbitrarily much memory and for arbitrarily long, and that the typical architecture of neural nets right now at least doesn't have that capability. But so the question would be, the phenomenon we see there is that with universal computation, we get to this threshold, and once you're above this threshold, there's no further you can go. And it could be the case that with things like language, human language, and so on, that the same thing is true. Once you're above that threshold, you can add more words to the language, and you can get more specialized, you can have more jargon and so on, but fundamentally you're there in terms of being able to have sort of an expression of thoughts that has the sort of this compositionality of thoughts can nest within other thoughts and so on, and that you're kind of, that there's no further you can go. Or it could be that, if we had 1 million words, we'd be able to sort of get to very different places. I think what we can see is there's a question of quantitative versus qualitative change. What we can see is that as we kind of formalize things with, for example, computational language, Wolfram language effort, so to speak, as we try and sort of formalize the world in computational terms, which has been our last 4 decades effort to try and represent the world in this kind of computational way, that it is certainly something as a practical matter where you can build much taller towers with that kind of formalized structure than you can if you're kind of just just using sort of plain language and so on. It allows you to know that your tower is not going to fall over. You don't, the foundations are solid, the bricks are hard, so to speak, as you build the thing up. So, I think another thing to sort of wonder, well, there's all these questions about sort of when we look at the future of, let's say, science, to what extent is AI going to, and this kind of neural net idea and so on, to what extent is that going to change, provide change to what's possible in science? It's worth saying there are things that are the whole using computation to represent and formalize ideas that turn into science. That's clearly a winning thing, and that has a long way to run, so to speak. And there are pieces to that. Once you formalize things computationally, there are kinds of things you can do that you couldn't do before. Like you could say something like, let's enumerate all possible theories of this. Let's enumerate all possible systems that do this or that have this or that structure. This is the area that I like to call ruleology, the study of simple rules, let's say, and what they could possibly do. Or equivalently, let's enumerate all possible chemical structures and see whether any of them do this or that thing. Let's enumerate all possible algorithms of this type. Let's see whether any of them do the thing we want. That idea of kind of ruleology and exploring the computational universe, it's not a very AI-ish thing, because it's a thing where you're really just computing out there. But perhaps then the question is, can AI help you to figure out, when you're searching this big space of possibilities, can it help you to say that's a more fertile area than that, and so on? That's one thing it could do. Another thing it could do is be able to say, once you've got a candidate thing, oh, I can predict more quickly that that's hopeless or that's interesting to look at. I mean, this type of thing, there are endless efforts to do drug design, for example, using sort of AI-ish methods where you're enumerating, and sometimes you're enumerating, sometimes you're selecting. I mean, you can use the AI. In a sense, it's very easy to get the AI to be creative, because you just throw around a number and you say, let's put the molecules in this, put the atoms in this configuration, and let's see whether that's a candidate. Now the question is, are you arranging it so that whichever way the dice comes down, you'll always get a viable candidate, or at least a plausibly viable candidate? And for that, it matters sort of what the underlying model of what these molecules might be like is. And if you set the parameters up correctly, then however you pick them, you're going to get a reasonable molecule. And that's a sort of AI-ish thing to do, to kind of figure out what's a reasonable parameterization so that you can then drive it with ruleology effectively, and just start enumerating things. So, I think there are questions like that. I mean, I think another type of question is, if you're solving math problems, like there was recent announcement about geometry problems, doing geometry proofs. If you say, well, is there a point at which human geometry proofs are kind of, we kind of know how to do those, because we've seen enough examples that we can kind of piece the pieces together. And for the level of things that are human relevant, we can just say, yes, we've seen enough examples, we can just see what to do. I think the question of sort of, can you always do, well, geometry is a special case, because geometry is a decidable mathematical theory, Euclidean geometry is, which means in principle, you can just, for example, turn it into an algebra problem. We can do that in both language and Mathematica. You can sort of turn it into an algebra problem, you just grind it, and you can get to a result. It might take a while, but you can do it. There are plenty of other places in mathematics, even in arithmetic. You say, I've got this equation that involves just integers, and it is, x cubed plus y cubed equals z cubed plus whatever. and say, find X, Y, and Z so that satisfy this equation, there is no upper bound in general on how far you have to look to do that. That's a undecidable theory. And so that's a thing where you can't guarantee. If you say, well, is it conceivable that I could just sort of close this off by finding enough sort of rules for how to do it, and that then I'd always be able to do it in limited time? The answer is no, you can't do that. So, but I mean, there's this question of, if you want to achieve sort of human level performance on some particular task, to what extent, sort of how many parameters do you need to be able to do that? How much training material do you need to be able to do that, and so on? And to what extent are there kind of thresholds of oh, it doesn't work at all, versus it's sort of achieved human level or something? And you might have thought this was a surprise with things like ChatGPT. You might have thought that as you kind of added more neurons or whatever else, added more training data, the thing would progressively get better. But in fact, that's not our experience. In fact, our experience is it was really crummy until it reached above a threshold, and then it looked really good. Now, is that a phenomenon of the thing itself, or is that more a phenomenon of our perception? I mean, it's kind of like you could say, I don't know, this is, what's a good example? I mean, when something kind of is good enough that we can really use it, versus it's kind of a little bit too crummy. What is a good example of that? There must be plenty in sort of mechanical kinds of things. I don't know, if you have an automatic screwdriver or something, where the thing doesn't quite have enough, can't quite exert enough torque to be able to screw that screw in or something. It's like, well, that was nice, but it doesn't quite make it for the purposes I have, because typical screws in a piece of wood or something require this amount of force, and it doesn't really quite make it. And so I might as well just throw that device away. And as soon as it's above the critical torque level, then it's like, okay, great, it's going to work. And it could be the case that we don't really have a good sense for something like language of what that thresholding looks like. My own guess is that there are certain, once you've learned certain regularities, you're above that threshold. Like, for example, I could be below the threshold where I knew basic grammar, and I could be continually making up sentences which are just grammatically wrong. Cat, dog, chase, mouse. I don't know, cat, dog, red, big, was. Okay, it's we can, in some language, that word order might be fine, but I can clearly make up sentences which you immediately know are wrong, because they just violate standard syntactic grammar in English, for example. And there will be a point at which that no longer happens, where it's syntactically correct, that whether and how that threshold works is not clear. I think I was yakking on here about a lot of things and not really even addressing the question that was being asked, which was, I think, about feeding sort of the next level of AI things that were the experience of the previous level of AI. And I think that is both an opportunity and a danger, so to speak. I mean, in the sense that right now we are getting AIs that do human relevant things because we train them on human produced stuff. By the time we're training them on AI produced stuff, we've got this sort of strange sort of dynamics where, the AI thing is, if the AI thing was exactly a perfect model for humans, then training on AI-based stuff will be equivalent to training on humans, and it's all good. But assume that the AI-based stuff isn't quite equivalent to humans. For example, let's say we've got essays, and for whatever reason, intrinsic or kind of control, the essays are very bland that the AI produces. And then the next generation of AIs are trained only on very bland essays. Well, obviously then, over the course of time, as we train more and more levels of AIs, things just get blander and blander. And yet they won't say anything wrong. They might say almost nothing, They might just have platitudes, so to speak, but that will be sort of the direction. So I think it's probably true that anytime one is using one is modeling what the original sort of underlying training data was, one sort of acting as some kind of modeler, observer, whatever, of that original training data, the kinds of things that you're doing to be able to model those things are sort of reducing that training data. It's not the whole training data. You've made decisions. You've got what amount to biases, not biases of social or ethical relevance necessarily, they might be, but just ones that the model was of this kind, and so it tended to do this or that thing. And then you amplify that by going to more and more levels, and then it's more about what was, I think this is the point, it's more about what was in the model than it was what was in the original data. In other words, if you iterate many levels of, you're going to train from the results of the model that was trained from the results of the model and so on, pretty soon you're reflecting the model more so than reflecting the underlying training data or possibly reality. Now, you can imagine that in sort of the training of AIs, let's say you're trying to get them to train on what the physical world is like. Maybe they're robots. Maybe they can go and make measurements about the physical world. Maybe they've got grounding in reality, in the real physical world, that they can go and mine more training data effectively from the physical world. It's us humans have only produced a certain amount of stuff. You could imagine some terrible scenario where sort of the AIs have decided that they just need more training data from the humans. And in some kind of strange inverse matrix type setup, the AIs have just hooked up a bunch of brains, and the AIs are just sort of poking those brains, just saying, we want more training data. We want to see, what does this brain do in that scenario? What does it do in that scenario? Let's go explore all these different things. And you have this sort of brain bank that is providing the ground truth, so to speak, for the AIs, as the AIs might have ground truth provided by going and exploring the physical world, for example. So that's a rather awful scenario, I think, from our point of view now. I mean, you might say, gosh, if AI is going to be the next evolutionary level in the development of our sort of, well, I don't know whether it's a biosphere, but the development of sort of the future of us or something, that, gosh, you just want the AIs to be as well trained as possible to carry as much of kind of the human achievement as can be carried into sort of the future of what exists. I think it's I don't know, as just a simple human myself, I tend to be rather human-centered, so to speak, and rather not the idea of and I suppose it relates to a lot of sort of, in a sense, both personal and societal purpose, so to speak. Is it, does one think it's okay? If a civilization wrote down all its great discoveries and they were passed down through the ages, but the civilization was exterminated, is that okay, or does one feel bad about that? I kind of think as a human, one feels bad about that. As a sort of looked at from the outside, whatever that means, because I don't think it means much, you could say, look, you've got more knowledge, more abstraction, more abstract kinds of things that were produced, even though, sorry, the actual humans that produced it are long gone. It really depends on, and it quickly devolves into questions, and this is going to go sort of deep philosophy or something, into questions about sort of the purpose of the universe, and if it has one, which I don't think it meaningfully can be said to have one. But this question of whether it's sort of good enough to have these kind of engrams of abstract achievement, or whether what matters is the details of the actual humans. And I think the it quickly devolves into meaninglessness if you say that what is going to be left is just the engram, so to speak, without the actual humans and their experiences. I think it's that Yeah, so I mean, this question about if you let the AIs train the AIs and so on, my claim would be actually sort of interesting thing, because okay, in biology, there are sort of forces of natural selection that are informed by the world as it is. You know, if the climate gets warmer and things like that, there will be changes to the sort of forcing function of what is a successful species. And so the species, through natural selection, will tend to evolve, sort of fixed to the ground truth of the actual physical environment of the Earth, for now, at least, until we get species on Mars evolving and things like this, or on the atmosphere of Venus. That's a more interesting case, I would say. But in any case, we can imagine some interesting kind of natural or artificial selection of let's make microbes that live in the clouds of Venus and so on, and perhaps do interesting things, or things we think are interesting to them. But okay, so in biological evolution, there's sort of a ground truth from the physical environment. There's also a certain set of constraints associated with kind of the way biological organisms are put together. You know, unless you're going to jump away from proteins and things, we're fixed. We have a certain set of constraints about what can happen. Unless it's pretty hard for organisms to make wheels. I mean, bacteria have little flagella at the back and so on, but fundamentally, you don't see a lot of big organisms running around or wheeling around on wheels, because that isn't something that's particularly easy to make with, blood supplies and nerves and all this kind of thing. So it's there are these constraints about the construction of the organism, and there are constraints that are imposed by sort of the environment. Now, it could be the case that being a wheeled organism would be a fantastic thing for some environment that arises, but you probably won't get there because it's just not something that can be constructed from the components you have. But I think an interesting thing with sort of the AI story here is if you say train from the train, train in a big train of training, so to speak, that you will end up with something which is much more dependent on the underlying constraints of the construction of the AI than on the external environment. If you keep going back to the external environment and saying, what can we deduce from sort of the ground truth of the external environment, that's more like what has happened in biological evolution so far. I mean, by the way, we can imagine a similar situation in biological evolution if we're evolving, in a petri dish, or maybe even in tumors in humans, I'm not sure, where sort of it's in an environment where the environment is sort of fixed, and you don't get to sort of go back and ask more about the environment. And then it's more something which is constrained by the intrinsic nature of the thing that's evolving, so to speak, rather than by what's sort of imposed by the environment. But so my guess would be, if you go the sort of the chain of trainings of AIs, that in the end, it will be more and more evident that, you were using a transformer with this and that and the other characteristics in the system. Now you can say, well, how about if you evolve the architecture of the neural net? Sure, you can do that. I think then you will be recursing again to saying, well, what was the evolver of the architecture of the neural net and so on. I think unless you get to sort of external ground truth, I think that you are inevitably going to evolve. It'd be an interesting thing to actually study in detail, to evolve to something which tends to be which tends to reflect the sort of inner construction mechanism. Okay, that was a super long answer to that. Let's see. Well, okay, there's a whole bunch of questions and comments about AI here. Let me try and address some of these. But X asks, do you think anyone will solve the Riemann hypothesis in your lifetime? Let's talk about that for a minute, and we'll talk about whether the someone might be an AI, what that would mean, et cetera, et cetera, et cetera. Reminder about the Riemann hypothesis, formulated around, 1860 or so, by Bernard Riemann. The Riemann hypothesis is about this thing called the Riemann zeta function, and as it's stated, are all of the zeros places where zeta of S is equal to 0 are all of those at places where on the critical line, S equals a half plus I times an arbitrary variable, where I is square root of -1. So that's what the thing is. It's stated in terms of this sort of mathematical construct. What it really is about is the randomness of prime numbers. It's really something that relates to the density of prime numbers. And really the Riemann hypothesis asks, is there a certain degree of randomness in the distribution of primes? If there is that, then the Riemann hypothesis is true. If there isn't that, then there's certain regularities that we didn't think existed that within the primes. And I think when you look at the zeta function, you just sort of plot it out and you see it wiggling, it wiggles a lot. And the Riemann hypothesis equivalent to is when it looks at these wiggles, is there ever a minimum wiggle, a lowest point that's above the axis, that's above value equals 0? Okay, so when you see it wiggling, you realize this might be a hard thing to figure out because there's a lot of complicated wiggles there. Now, the real question, though, is what would it mean to figure it out? It really relates to questions about what is mathematics. And the kind of last century or so view has been mathematics is based on, you set down axioms, you say, these are the things that I assume are true. Euclid said that. These are the things I assume are true. Now let me, as a purely sort of mechanical process, see what I can derive from that. Now, that's a tricky thing because what do you assume is true? Like Euclid, for example, assumed his fifth postulate, assumed that no parallel lines can ever cross. And that postulate turns out to be, what's a fine thing to assume. You can do geometry on that basis as a constructive kind of thing, but it turns out it's not true for the physical universe. In the physical universe, space can be curved. That was sort of the discovery of general relativity. And that means that Euclid's axioms are just sort of this bubble out there that's not related as such to physical reality. And you can invent different axioms for mathematics. And you could say, well, somebody could say, well, I've got the Riemann hypothesis, and I'm going to choose these axioms for mathematics that include very obscure things about infinite sets and how they work and so on. And it's like, okay, with these axioms of mathematics, kaboom, we proved the Riemann hypothesis. You say, well, that was, or for example, worst case in areas of theoretical computer science, people sometimes assume the Riemann hypothesis. So you could say, well, I'm going to make an axiom system and I'm going to get something which is, almost assuming the Riemann hypothesis. Then if I prove the Riemann hypothesis, like, who cares? That was obvious. So the real question about proving the Riemann hypothesis is you've got to go from some axioms to prove the hypothesis. Now, it could be the case that the axioms that you typically use in mathematics for, let's say, arithmetic or something, that those axioms are just not powerful enough to prove or disprove the Riemann hypothesis. It could be the case that the Riemann hypothesis is something where, it's a thing where you could, with those axioms alone, you just don't reach that particular theorem, roughly. It's a little bit more complicated with the Riemann hypothesis because it has the feature that if you can show that it is undecidable, then it is in some sense true because of just the way that it's stated in terms of for alls and there exists and things like this. But roughly, it's fair to say that sort of it depends what, you have to ask, given this particular sort of low-level formalization of mathematics, and by the way, most mathematics that's done is not done down to its lowest level formalization. For example, when Fermat's last theorem was proved, the chap who proved it, I asked him, he said, what axioms did you assume? He says, I have no idea. I just did it using sort of common mathematics of the time, which is what everybody thought was the interesting thing to do, to say kind of what would be the, to say, can you just go mechanically from certain axioms to prove that theorem? That's sort of a different level of question, not one of such interest to most mathematicians. I mean, there are efforts in modern times to make proof assistants, computational systems, where you're kind of fitting together puzzle pieces, and you're saying, if you can fit this puzzle this way, then you have definitively proved this thing. But it's a really hard road to be able to do that. And then, even when you've done it, it's not clear what you've got, because it could be the case that, so what you have to claim is that something like the Riemann hypothesis, Fermat's last theorem, that there's a gaggle of possible axiom systems for which that a reasonable axiom system makes the thing true. And that if you tweaked the axiom system so that it wasn't true, lots of other stuff would fall apart. But that's a little bit of a trickier thing. Now, it could be the case that with the kind of standard level mathematics that don't go all the way down to these axiom systems, that you could prove the Riemann hypothesis. And I don't have a good sense. My own guess would be that you need to go down to this infrastructure level, that if in the end, it has a dependence on some infrastructure kinds of things. I will say about the Riemann hypothesis, there is a nice correspondence. There are sort of fairly simple to state mathematical problems like the 3n+1 problem. You take a number, if it's even, you divide it by 2. If it's odd, you say 3n+1. And then you ask the question, if you start off with any number, does that thing eventually reach sort of small numbers? It goes to 1 and 4 and things like this. Or does it sort of eventually go off and get bigger and bigger? If it always hits the 3n+1, it's going to get bigger and bigger. If it hits the n/2, it'll go down to something smaller. And it bounces around. You can make these plots, they bounce around all over the place. So it turns out there's a formulation of the Riemann hypothesis. It's partly due to, well, most of the real work done by a chap called Yuri Matusevich, long-term user of our technology, who's been involved in proving lots of interesting things about kind of what's decidable and what's not. But anyway, he kind of made a version of the Riemann hypothesis which can be stated in terms of these sort of iterations involving integers. I tried to clean it up a bit, got a simpler version, which actually I think seemed to people at some point so bizarre that how could this possibly be right? But I think it is, and it's just it's a one line of language code, and just says if this iteration n goes to blah blah blah, if that iteration always terminates, then the Riemann hypothesis is true. And so you've reduced it to this problem about sort of iteration of integers, and that kind of makes it a little bit more it brings it a little bit closer to these kinds of questions that are more about kind of going down to the low levels of axioms, and a little bit less about kind of, can we construct this nice geometrical picture that allows us to use sort of traditional mathematics to go and work through different kinds of things. So I think the answer is, my guess would be that the Riemann hypothesis might be proved to be undecidable from certain axioms. That's a thing that might happen, fairly soon, to know kind of the narrative story, from sort of some common idea of mathematics that isn't as such the axioms. I think that's a more challenging thing. Let's see. Oh boy, there's a question here from Jamie. Will AIs, let me take a quick comment here from RBS. Aren't there thousands and thousands of papers written that assume the Riemann hypothesis is true? Yes, absolutely there are. And let's see, I mean, the status of those, many of them are algorithmic papers that say this algorithm will be correct, this randomized algorithm will be correct if whatever. And my guess is, I haven't really thought this through properly, but my guess is that this whole question about what axioms you're assuming to get the result, that probably relates to, particularly when it's randomized algorithms, that probably tangles itself up with where did the randomness come from? That you say, well, I pick these things at random, and with overwhelming probability that approaches 1, this or that will happen, that somehow the axiomatization of that randomness will be sort of entangled with the axiomatization you're using to prove the Riemann hypothesis. That would be my guess about how that will work. let's see. Jamie's asking, will AIs be the ones to explore space? Well, I mean, it depends. I think that, in space is not very human friendly. It's the timescales, the speed of light compared to, and the distances between stars compared to human lifespans, it doesn't look good. It's, you want to get to the nearby star, it's going to take you many current human lifetimes to do that. And so, well, what do? Well, you can sort of dehumanize the humans at some level. You can say, okay, let's make the thing that's worked in science fiction forever, but we don't yet know how to make work in practice, cryonic suspension, so to speak. Let's make that work. And then sort of we kind of we freeze the humans, and then they wake up in 50,000 years and they're at Alpha Centauri or something. In a sense, that's in that sense, yes, the humans can explore space if we manage to make that technology work, which my guess is one will be able to. I think it will be non-trivial to have the interstellar dust interstellar dust particles that hit the spacecraft, not over the course of 50,000 years or whatever, not destroy any material we put in place. But let's assume that's also solvable. Let's assume there's little robots that go fix things and things. But in a sense, it's like, well, yeah, we got a human to Alpha Centauri in 50,000 years, and so what, so to speak. And we could also say, well, we got some kind of AI to Alpha Centauri in 50,000 years. And again, it might be a so what, because this relates to sort of, again, to these things we were talking about before, about, you can create a thing computationally, you can do a thing, but does it relate to anything that we humans actually care about? I mean, I think that it's worth remembering that the one way that we get to kind of explore the universe without going to all that trouble is through things that go at the speed of light, whether it's light itself, whether it's gravitational waves, whether it's maybe neutrinos that go at least really close to the speed of light. These are things where they're they are ways to sort of see different parts of the universe without physically going there. In other words, how important is it to see with your own eyes Alpha Centauri versus how important is it versus if you get photons from there that we can receive here, is that a thing one can do? And then, I think it's worth remembering, it's kind of ironic that for a photon, because it's going at the speed of light and time is infinitely dilated at the speed of light, to a photon, no time passes. From the time the photon is emitted to the time the photon is absorbed, that's, just a moment. There's no time has passed. So photons that were emitted right at the beginning of the universe, or at the point where the universe became transparent, 100,000 years or something after it began, where there are photons that are just sort of going through coming towards us, and eventually some photon from the cosmic microwave background that lasted 14 billion years of our time and finally got absorbed by some detector. It feels very sad that it lasted 14 billion years and then splat, we detected it in some detector of microwave radiation. To the photon, no time will have passed. To the photon, if the photon was kind of, if we had some kind of assembly of things that was if we could imagine a mind made of photons, so to speak, then no time would pass for that mind between the creation of the mind and the destruction of the mind, so to speak, at a time which for our minds is vastly later. So, I think there's this question of we're going to explore the universe, we're going to send out sort of AI probes, they will kind of go out and about in the universe, and they'll arrive places 100,000 years from now or something. I don't know. That's a complicated issue. How one feels about that. I mean, it's kind of like building the pyramids and putting things in there that were sort of intended for the afterlife, but end up being relevant for 4,000 years later. And how do you feel about that? That process of putting things out there into the universe. I have a number of friends who've been involved in sort of putting things out into the universe, so we at least have planted our flag on the universe even long after we might be around or not around, and so on. So I think it's but if one's asking the question, for example, within our solar system, will it be the case that it's we can have robotic spacecraft going and exploring things? Surely the answer is yes. There is a certain sort of coolness factor to having the actual humans show up on Mars or whatever else, rather than just, oh, it's a robotic probe and it's sending data back, and we can get, even if we can get very high bandwidth data back from it, it still feels cooler and feels more us related if there's, a friendly human, so to speak, who went there, rather than just a robotic probe. But I think, it's clearly vastly easier to have, it depends a bit on one's view about sort of the value of humans versus the value of robots versus whatever else. I mean, if, in some, to my mind, very undesirable world where, you say, well, humans aren't that valuable, we can send a bunch of them off to Mars, maybe some of them will make it, and, they're cheap, so to speak. That will be a different world than fortunately than the one we seem to live in, where it's where the calculation of what's it plausible to do is different. I mean, there are plenty of places in the world today where it's like, well, we could have a factory robot do that, but why bother? Because we can have a human do it sort of for the same price type thing. And I think, you can imagine the same kinds of things with respect to robotic probes versus humans. And insofar as you put sort of the value of human prosperity and life for the astronauts or whoever else very, very high, it makes it much more attractive to send the robot out where, it's kind of just money if it blows up, so to speak. Let's see. Yeah, well, RBS is commenting, if only we could just send, okay, if on Alpha Centauri we had a sort of friendly, cooperative, whatever, where we just send a light signal out there, and then a 3D printer starts up on Alpha Centauri and makes the thing that we want to make. And then it goes and, does its study of whatever we want to study, and it sends back this wonderful picture of this totally alien thing that we don't recognize as anything like life or whatever else, some complicated chemical process that we say, that's kind of interesting. I wonder what that means, so to speak. Yes, but I think that's kind of a, we don't have a way to do that. It's an interesting question whether we could, in a sense, whenever right now, we are taking passive information from, for example, exoplanets. There's light from a star. It maybe goes through the atmosphere of the exoplanet. Maybe we get some wonderful spectroscopic conclusion from that. But we're not, and we're far from being able to say, let's shine a laser in the direction of that exoplanet, wait 8 years or something and see what comes back. We're not in a position to do that. The energetics of that don't work out even close right now. I mean, the fundamental problem there is if we could keep a beam of light sort of perfectly collimated, then we might be able to do that, but we can't because of the phenomenon of diffraction. It's inevitable that it will spread out, and we can't. And so that idea that then we have to put incredible power into it so that even with the sort of inverse square law of it spreading out, we'll still get something reasonable back. I mean, to give an example of actually probably the sort of the furthest out active things like that are you send a signal to which one is it? Voyager is still in contact, or Pioneer? Voyager, I think. Voyager. Yeah. So you can send a signal out to the Voyager spacecraft, and it will do something, and you get data back. That's kind of like we put the 3D printer on Alpha Centauri, except it isn't even close to Alpha Centauri yet. But so the question would be, is there a way without humans having put something at the place where you're having a receiver, could you imagine a situation where there's a thing out in the distance, so to speak, that could receive a light signal and do the useful thing with it and then send the data back? We don't know how to do that right now. And but that's, I mean, one could imagine that, and that would definitely make it even less sort of attractive to send out that human-built piece of material stuff. I mean, in a sense, what one's proposing doing is sending out human-built photons, but rather than human-built physical objects with little pieces of metal and so on in them. Let's see. You know, I mean, I have to say, in our models of physics, to us right now, photons look like featureless. You've either got one or you don't. In our models of physics, photons are probably made of this kind of complicated structure made of this network that represents the structure of space and the structure of everything in the universe. It's kind of like saying, I've got an eddy in my water and I can see that eddy and it's just an eddy, but that eddy is ultimately made up of a bunch of molecules underneath. And so one could imagine that sort of a photon, right now, we only think the only thing that matters about a photon is its energy and its momentum. That's the only thing that distinguishes one photon from another is its energy and its momentum. There's no labeling of a photon beyond that. And well, actually, that's more okay. That's basically a fair statement. It's a little complicated. Which is the photon, and that you'll end up with two of them, and they have different effects and so on. And the question is, do they exist physically or do they exist in branchial space? And that's the whole story of quantum mechanics and so on. So that gets complicated. But in a first approximation, sort of a photon is a photon. And it's kind of like a black hole in current theories of physics. It's kind of like a black hole. All that matters is essentially the same thing: energy, momentum, and there's a few other parameters that matter as well, the spin and the charge and so on. But to the outside of the black hole, that's all that matters. Inside the black hole, it could be the case there was some whole civilization that was, whose planet was crushed by some collapsing star and so on, and that's inside the black hole. But from the outside, you don't see any of that. And might be the same way with photons. Maybe there's no way of sort of cracking open the nut of the photon, so to speak, and seeing what's inside. In the case of black holes, we think that quantum mechanics, in some sense, can crack open the nut and see what's inside. And so this question of, okay, you've packaged things in a photon that's going at the speed of light and so on, is it possible you could sort of crack open that nut and see more detail about it? It's faintly conceivable given our models of physics. It's certainly something far away from what we know how to do at the present time, or even it's this question of, well, are all photons really the same? Right now we don't have any way to distinguish them, but that will be one possibility. That will be one bizarre possibility for a sort of additional channel of communication. I don't hold out that much hope for that, but I think that's a conceivable thing. I mean, something people are always commenting on is when it comes to, have we met the aliens, so to speak? And I always think that's a very poor question, because the details of us humans, if there was something in the galaxy that was just another, humanoid carbon life form type thing, we meet them and we say, yes, you're a humanoid carbon life form or something, we recognize what it is. But if what it is something that involves chemical reactions involving manganese and niobium doing this and that and the other and producing very complicated patterns, which to the inner experience of the manganese niobium thingy is like, look, we have this amazing civilization. But we look at it and we say, that's some weird chemical reaction which we don't understand, and who cares type thing. So I tend to think that the problem of sort of alien finding is a problem that there are many complicated things going on in the universe. They're just, in the terms of our physics project, for example, they're not close enough in real space to us that we can readily interpret them. But in any case, the thing that's often sort of a staple for science fiction and so on is, imagine there's a new way to communicate in the universe, which is basically saying, imagine there's a new feature of the universe that we get to bring into our perception. Like, we've had eyes since the trilobites or something, I don't know, whatever it is, a solid few 100 million years, life on Earth has had eyes. But life on Earth doesn't have neutrino detectors. Life on Earth doesn't have gravitational wave detectors. We've built those things as pieces of technology. Our species has built those things, but that's something where we get to see a new feature of the universe when we do that. And one might imagine, okay, well, guess what? If only we had managed to tap into the gravitational wave sort of internet, then we would discover the aliens. Now, in some sense, things like that are true, because this point that there's a lot of complicated stuff going on in the universe, and what you notice depends on sort of how you can do the noticing. And so that's something where you can expect, yes, once you know about gravitational waves and you can detect them and so on, you'll be able to see complex processes going on in the universe that you weren't otherwise able to see. And you could say, well, we've detected sort of the alien intelligence. I might say that, the weather on Earth is an alien intelligence. It doesn't happen to be very close to our intelligence, but it is something that has the same kind of computational complexity that our brains have. Let's see. It's a question from Imagination here. Do you think Ray Kurzweil's longevity predictions are likely to happen in our own lifetime? I haven't talked to Ray in years, actually. So I don't know how he's doing on the longevity scale. But I remember having lunch with him a number of years ago, and was impressed at the number of pills of different kinds that he took, along with one piece of lettuce or something. So, who knows? Maybe that's a winning solution. I think that the question of what will happen with sort of human longevity it's an interesting one. I mean, we've been in many countries, sort of the life expectancy has been increasing by about a third of a year per year for the last 70 years or so. I think most of that is cardiovascular kinds of things, that things which are essentially mechanical, people can detect and so on. I tend to think, and it's certainly my own personal sort of approach to this, is the first step is detect things. Do all those tests, make all those measurements. If they all say it's all fine, then, assume it's going to be fine. But by doing all those tests, you get sort of an early warning of what's going on. I mean, it's kind of like, how did aeroplanes or general anesthesia, two examples where sort of there have been great advances in sort of their effectiveness and not crashing and not failing type thing over the course of years. And I think the thing that's really been the big driver of those is better sensors, better kind of awareness of what's going on. Is the tail of your airplane about to fall off? Well, you might have some sensor that would tell you that, rather than just where you have to wait and see what happens. So I think the metal fatigue detection or something from whatever, but different kinds of things. But the point is, so I think one, that's surely a driver of longevity, but it's not going to solve the problem, because that's just saying, detect things early, maybe you can patch them, you can fix them if you detected earlier. That still is the case, apparently, that life eventually wears out. Now, at some level, there are plenty of organisms where kind of that organism buds off another piece, and the bud kind of keeps going, and the organism's gone on for a gazillion years. The organism, in some sense. You could say, but it's not the same organism. But it isn't the same of us either, because our cells are continually turning over. Okay, there are some cells like nerve cells that don't turn over, at least not at all quickly. But the is it us? Well, our skin cells, our gut cells, whatever else, blood cells, they're all turning over fairly rapidly and being replaced by new cells. And so, I think there's this question of, but we think, the part of us that is critical to the usness of us is mostly brain type things. Whether that's really the ultimate story is not so clear. I mean, I don't know how much of the usness of us depends on things other than brains. It might depend on the endocrine system, might depend on the immune system, might depend on the gut microbiome. Who's to say? Those things you say, well, those aren't really relevant, but they might change. For example, your approach to life might be different depending on sort of, hormone levels that are produced by something that has little to do with the brain as such. So it's not completely clear what the package that you need to sort of maintain the usness actually is. But I think when it comes to, maintaining the whole package that, supports the brain and all these other systems, that's the question is, can you do that? And sort of, how will one increase longevity? Well, the first question is, why do we age to begin with? And that's not completely clear. I mean, it's, there are different sort of things that go wrong, and there are telomeres that fall off the ends of DNA, but then they can put them back on again, the enzymes can put them back on again. Then there are sort of oxidative damage, things essentially just burning up. And there are sort of deposits of this or that get produced, all kinds of things. There are sort of tanglings of the DNA. There are all sorts of different things that go wrong. Obviously, they can be fixed because when you go to the next generation, those things are restarted. And it's not obvious that you can't take, the things that you have right now and kind of restart them from stem cells, for example. There's increasing success in kind of taking first thing was taking a cell that exists, some random skin cell or something, and reverting it back to something that will be a cell that can differentiate into anything, just like our original, fertilized egg or something cell can differentiate into all of us, so to speak. And so that's it's clear that it is possible to turn the clock back because it happens with every successive generation. So now the question is, can you sort of turn the clock back within an organism? In a sense, can you rebuild the plane even as the plane is flying, so to speak, with us organisms? And we don't know yet. Is it conceivable? Yes, I think it's conceivable. I mean, the very fact that was discovered, what is it, 15 years ago, 20 years ago, 15 years ago, I think, of how to go back from a sort of a specific cell to something that is a stem cell that has the potentiality to turn into lots of different kinds of cells. That was only discovered fairly recently. And I know there are experiments going on of, can you kind of cure aging by just sort of having cells be fresh cells in some way? And, there are things where you say, when there's cells that didn't make it and that one kind of became senescent, when that cell was sort of died off, let's get rid of those cells, and then maybe there'll be more cells get produced that don't have those same aging characteristics. I think but it's also the case, it's a very strange thing that there is so many clocks in biology. I mean, the thing that always is a little shocking to me is you use a facial feature recognizer like the one we have in Wolfram language, and it'll tell you, it takes a picture of you and it'll tell you how old you are. And it's like, really, and it gets it right quite accurately. I mean, I was thinking for me for a while that I might have been in the training set for the machine learning classifier that figures out ages, but I don't think that's what's going on. I think what's going on is that there are gradual changes in facial structure, just as there are gradual changes, eventually by the time you're like 40 years old or something, the plates of the skull fuse and so on. There are things that happen over the course of many decades and which sort of inexorably happen, and which, by the way, the AI can notice, even though we humans don't so readily notice these things. And so that's sort of an inexorable clock through life. Now, that particular thing of moving around facial features and so on, and, you know, pieces of cartilage getting bigger and whatever else is probably not relevant to whether you live or not, but it's certainly a kind of a sort of a reminder of the fact that there is an intrinsic biological clock. And what is needed to divert that biological clock, we don't know. I mean, and of course, with things like tumors, what's happening there is that sort of the usual sort of clocking and limitations on growth and so on that exist in biological organisms, they have been removed, and we're kind of back to a form of life before we had sort of individual organisms that grew to fixed size. It's just like, just keep growing. And that turns out not to be very compatible with, with organisms that were at our stage in the evolutionary process, so to speak. So, but what it takes to get into something which sort of grows like us, but doesn't go out of control like that, it's almost one of these undecidability problems. You set up a certain set of conditions in your molecular biology. Is it going to be something which sort of does the right thing, or is it going to do something computationally irreducible and unexpected and do the wrong thing and, for example, start sort of growing forever or some other bad thing like that? But so, I think, look, in the end, there will be human immortality. I don't think there's any fundamental reason to think that that's impossible. What exactly it will mean and how much is sort of turned over in that process, what it means is you kind of get to have a biological organism that sort of has the same memories and can remember from 300 years ago and so on, my guess is that will happen. And how much of that will have been sort of, oh, and you, by the way, have a digital sort of assist that's connected to, forget having actual organ X. Let's just have the kind of technological version of organ X. Why bother to have an actual liver or something? Just have this kind of artificial one that sort of plugs into is plug compatible with the biological one, and maybe much of what you have ends up being that artificial technological solution, and then you have to ask, what does it mean to have human immortality in the case where almost everything has been replaced by something that isn't really terribly human? And of course, that gets even more complicated when you're replacing pieces of brains by sort of the digital assist, so to speak, or the neural net, the artificial neural net that sort of, oh yes, well, something went wrong with some piece of the hypothalamus, so we replaced it with some artificial hypothalamus. And then, and then it's like, how far does that go? And at what point do you have human immortality versus essentially just, or I say just, but it might be, that this quotes artificial, this technological immortality. I'm certainly hoping as a person who's getting old myself, I certainly hope that the advances that might happen that would get one to the point where the life expectancy is increasing at more than 1 year per year, so to speak, so that it sort of goes to infinity. That happens sort of soon enough to not to not sort of exit oneself. It would be great. I mean, the other opportunity is the whole cryonics story and the ability to sort of have a pause in and sort of freeze everything until for a better day, so to speak. I think the challenge with all of these things, the challenge with that one is the discontinuity of experience may, if one's been around and exposed to the way that technology is evolving and so on, we're not that, one isn't, if you took the me from 1965 or something and brought me to today, there'd be lots of things where I have no idea how this works. What the heck is this? it's the world has changed because of technology primarily, a little bit because of social kinds of dynamics as well. But one might sort of say some things that will be terrible today, or say some things that will be charming today, from jumping from 1965 or something. But I think that that dynamic of kind of if you are continually around and sort of paying attention to the development of the world, you're going to be sort of still in your time. If you kind of were frozen for 100 years and then come back, then you're not in your time, and it's not completely clear how that plays out. Let's see. Somewhere off comments. Would it make sense for alien AI civilizations to broadcast radio or other signals with information about how to build an AI that can propagate in the universe faster than material space travel? Yes, but the thing that's so difficult is it's so hard to go outside of one's current human purpose, the things that have been sort of, bashed into us by our struggle for life in biological evolution, et cetera, et cetera, et cetera. It's so hard to kind of go to the kind of the abstract purpose of, now it has to be said that if whatever you do causes you to not exist, then there's nothing more to say. So there is a certain sense in which sort of the propagation of something and making more of it exist is a self-fulfilling thing that has to happen. So, I suppose that's an argument for why one could say that, let's see, what will be an extreme thing to say? One could say that, look, all of the, what could I say? Something like all of the interstellar grains that have all these particular molecules on them that we can, that we get radio signals that show us that this molecule exists, and this slightly weird molecule we never bothered to look at before exists. Gosh golly, there must be an intergalactic conspiracy, or at least interstellar conspiracy, that's putting these particular molecules on these grains that we will detect, and that we'll say, gosh, that's an interesting molecule, let's go make that molecule here. Now, that isn't our usual interpretation. Our usual interpretation is it's just physics that's putting these molecules on these interstellar grains. But I think that this it's just physics argument is a complicated one, because look at what our brains do. It's just physics. It's physics where we say it's packaged in a way that's very special to us, et cetera, et cetera, et cetera. But at some level, it's just physics. All right, maybe one more question or comment. A bunch of comments here about diminishing returns, Fu says, related to AI and machine learning. Hans comments, AI will create this time of step function upwards in everything, but that may not be the case due to diminishing returns. Yeah, well, I think it's an interesting question. To what extent, what we've seen sort of observationally in the technologies, we've seen, the big jump in 2012 with image identification and so on, image processing, slightly less heralded big jumps in speech to text, for example, big jumps in language generation and so on. It seemed like there keep on being these sort of jumps where something gets to the point where it wasn't possible and now it's possible. And there's the question of, well, there's a certain set of things we humans do and we can kind of check them off. Could we do that one? Could we do that one? And so on. And I think and then there's the question, well, what about the things we humans don't do right now? And that's where things get challenging, because, it's very easy to make a computational system that does a lot of stuff that we humans don't do. Problem is, it's not clear we humans care about it. I mean, in my life, I've spent quite a lot of it studying ruleology, kind of the study of simple rules and what they do, kind of what's out there in the computational universe. your average, cellular automaton with all these rules, very simple rules, often very complicated behavior. You look at it and I say, that's pretty interesting, but I can't really humanize it very well. I can't really say, and that's why, it makes my, me have a better lunch type thing. It's much more abstracted from that. And I think this question about once we know there's certain things we humans do. Now there's the question of what else is out there in the computational universe. And there's a lot out there in the computational universe. But the history of civilization, the history of sort of intellectual history, is about making these small moves away from what we've already done, sort of building on the tower we've already built. Then we go to the next step. And there's this sort of vast expanse out there of what's computationally possible. And most of it, we humans, as of today, would look at it and just sort of shrug and say, we don't care. I mean, I think we care because I care about rheology and studying this computational universe and sort of the science of that. But in general, I would not be able to say that there's sort of immediate everyday applications of what you see out in the computational universe, except things that are pretty close to where we've already gone so far. So I think this question of sort of, can the AIs do, they go out into the computational universe, what do they find? I think the limiting factor there is mostly what do we humans care about? That is, we can, and that becomes sort of what are the humans going to do? Well, the AIs can zoom off in any direction. The AIs are, fast driving cars or something, but it's not particularly useful to have a fast driving car unless you have unless there's a human driver who's deciding where the car should go. I mean, the disembodied fast driving car can zoom off in random direction in the desert or something, but it's like the humans are probably going to say, who cares? The place where the humans fit in is in this, so which direction do we want to drive in? And I think that's something where when people wonder sort of how do humans fit in to the world of AIs, yes, the AIs can provide the fast driving cars, but it's still got to be one's got to have choices which are for us humans insofar as we care about what we perceive in the world. That has to be determined by what we humans choose, so to speak. So I think they're both practical technological things about these thresholds associated with different kinds of things you can do. Then there are these so what does one care about doing that one gets into? And, I do think it's still sort of an open question if what does one care about doing? We care about, for example, making human language. Let's say there's another level of thing there that is, I don't know, let's say you have sensory information, not from just you and your eyes and your fingers and so on, but you have sensory information in detail about the whole world. Now, in a sense, we already have that because, we're looking at the web and so on, and we're getting, live streams from all over the place and all that kind of thing. But let's say we were able to have sensory information, sensory input that really was looking at every, Internet of Things sensor everywhere in the world. And maybe there's a different level of description that we can start to apply. Human language, maybe we could say, is relevant if what we're talking about is the kinds of things that we as sort of humans walking around and, whatever, about, 5.5 feet tall or whatever it is, that we experience. But there's a quite different level of thing that's a super, not language-like, but who knows what it is, some way of organizing things that's relevant if you are seeing every sensor in the world, so to speak. I mean, it's you might say there's certain kinds of things that are worth thinking about if you have eyes and you're getting visual data, different things if you only have touch, for example. All right, I better go back to my day job here. But thank you for a lot of interesting questions and comments today, and got me to think about a bunch of things I haven't thought properly about before. So thanks very much, and look forward to chatting again another time. Bye for now.